video, we have learned about power method that can be used to determine the largest or the dominant eigenvalue of a matrix A. And today we will discuss about the shifted power method, where we can use this method to determine the smallest eigenvalue lambda n using a method called shifted power method. And then so far we already know that power method to determine the largest eigenvalue, and for the shifted power method we can know the smallest. So let's say our matrix is 3 by 3 matrix. A is 3 by 3 matrix. So that this is, by using our power method, we can get the largest eigenvalue. Let's say it is lambda 1. While for this shifted power method, we can get the smallest eigenvalue, and let's say it is lambda 3. Or maybe some of you will say either one, but we must know that the power method to find the largest eigenvalue, while the shifted power method to find the smallest eigenvalue. So there are some steps in this shifted power method. The first step, we need a shifted factor, and this shifted factor actually is our dominant eigenvalue that is obtained by using power method. And then by using this shifted factor or this dominant eigenvalue, we can find a new matrix by using this formula. We can have a new matrix B is equal to matrix A minus P multiplied by identity matrix. And then after that, once we have a new matrix B here, we can use the dominant eigenvalue for this new matrix B by using the power method that we have discussed yesterday. And then after that, we can know that the smallest eigenvalue can be obtained by using the formula that I underline it now. Lambda n is equal to lambda b plus our shifted factor p, or plus our dominant eigenvalue for matrix A. And then after that, we also can find the associated eigenvector, which also is equal to eigenvector for matrix B that is obtained by power method. And here there are some important properties. Properties number 1, if we have a 3 by 3 matrix, and then the sum of all eigenvalues lambda 1 up to lambda n also is equal to the sum of the diagonal element of our matrix. And also property number 2, if we have a n eigenvalue and it also equal to determinant of the matrix A. And then he said that by knowing the dominant and smallest eigenvalues, we can use these above properties to determine the second eigenvalue. Meaning that, let's say the dominant here is lambda 1, and the smallest eigenvalue here is lambda 3. Therefore, we can get our second eigenvalue lambda 2 by using property number 1. Okay, now let's look at the example 6 here. We must consider the matrix A, this one, and we need to show first, by using the Gauss-Gorin theorem, show that all eigenvalues of A are positive. So what we have discussed yesterday, for A here, we need to use our information or knowledge that we already know, that the Gauss-Gorin theorem. And by using Gauss-Gorin theorem, we can get the radius R1 is equal to absolute of our element in the first row. So 2 and -1. 2 plus absolute -1, and we will get 3, while the center C1 is equal to Z minus the element of our diagonal in the first row, which is 4. And it must be less than 3. And from here, we know that our center is 4, while the radius is 3. And then we move on to the second row. R2 is equal to absolute value 2 plus 1, which is also equal to 3, while C2 is equal to Z minus 6 less than or equal to 3. And from the row 3, we know that we can have a circle that center at 6, while the radius is 3. And then for the third row, R3 is equal to absolute -1 plus absolute 1 is equal to 2, and the center of the radius, the center of the circle 3 is equal to Z minus 12 less than 2. And from the third row, we can know that we can have a circle that center at 12, while the radius is 2. And then after that, we can draw a little bit circle to show our we can have 3 circles that show our eigenvalues must be in that range. So the first one is centered at 4. Let's say here is our 4, and our radius is 3. So meaning that, let's say here is 0, and let's say here is 7, so that we can have a circle with radius 3, center at 4. And then from the second circle, we can have the center at 6. So let's say here is our 6. And then the radius for the second circle is 3. So now we can have from 3 to 9. Let's say here is our 9. And then we can have the second circle like this. And then while from the third one, we can have we will have the circle that radius at 12. Let's say here is our 12. And the radius is 2. So now let's say this is 10, while here is 14. And then we can have a circle. So that we can see here our lambda, which is our eigenvalue, must be from 1 to 9 union 10 to 14. I'm sorry, it should be 1 here, not 0. Okay, this is the solution for A. For B, we need to use power method to compute the dominant eigenvalue lambda 1 of the given matrix A and its associated eigenvector V1. And we must use this V0 that is given here, and we must stop our iteration when our epsilon is less than 0.05. So now we will use a power method let's say now we want to write our A is equal to 4 to negative 1 to 6 1 negative 1 1 12. And then we know that for the power method we can have K, and then we must find AVK, and we also must find our MK plus 1, which can be obtained from the formula. So this is the table that I showed yesterday. So from K equal to 0, we have V0 that is given, which is 0.5, 0.8, and 0.5. And then we can determine our A, V, 0. So for K equal to 0, this is our calculation. For K equal to 0, we need to determine AV naught is equal to, our A is 4 to negative 1 to 6, 1, negative 1, 1, 12. Multiplied by V naught that is given 0.5, 0.8, 0.5. And if we insert all these two matrices in the calculator, we will have 3.1, 6.3, 6.3. So that from here we know that our MK plus 1 is equal to M1 is equal to 6.3. And then by using this eigenvalue M1, we can know that our V1, eigenvector V1, is equal to 1 over M1, 6.3, multiplied by AV0, which is 3.1, 6.3, 6.3. And we will have our V1 is equal to 0.49211. Like this. Now we can substitute in the table. Our AV0 is equal to 3.1 here, 6.3, 6.3. And then our mk plus 1, which is our m1, is equal to 6.3. And we also need to determine our epsilon, where the epsilon criterion that I showed you yesterday is mk plus 1 minus mk. So of course, this is not, we cannot find it. But I know that some of you notice that our stopping criterion now is mk minus mk minus 1. So now it is actually, they are same. I mean, same here. We want to use either one of the stopping criteria. So now let's say we want to use stopping criteria mk minus mk minus 1. Okay, and now we will have our mk. To use this stopping criteria, before that we must have what is our mk, otherwise we cannot use it. So here we can have mk column, and then now let's say now we want to use mk minus mk minus 1. So of course we don't have, so now our k is 0, we don't have mk, so that we also cannot find what is the value of our mk minus mk minus 1. Okay, and now for k is equal to 1, we need to calculate, or we know that our v1, which is 0.49211, and then we need to calculate a v1. K is equal to 1, we can calculate a v1 is equal to, again our matrix A is 4, 2, negative 1, 2, 6, 1, negative 1, 1, 12, multiply by 0.49211, and then this one we will get 2.968, 7.98, 12.508. And from this one we can get our mk plus 1 is equal to m2 is equal to 12.508, and then we can get our v2 is equal to 1 over 12.508 multiplied by AV1, which is 2.968, 7.984, 12.508, and we will get 0.237, 0.6381. And then we can put all our calculation here in the table. Now we have AV1, which is this one, 2.968, 7.984, 12.508, and MK plus 1. Now we can get, when K is 1, we can get M2, which is 12.508. And then now we can calculate our stopping criterion. MK plus 1, now it is M2 minus M1, which is 6.21. And now our M1, what is our M1 here? It is 6.3. And then here M1 minus 1 is M0. Again, we don't know. So maybe we can put 6.3 also. Okay, so now next is we proceed with k is equal to 2 because our epsilon is still greater than 0.05. Now for k is equal to 2, we need to calculate k is equal to 2. AV2, where V2 is given by this one. 4, 2, negative 1, 2, 6, 1, negative 1, 1, 12, multiplied by 0.237, 0.638, and 1. And then what you will get is 1.224, 5.302, 12.401. And from here, we can have our MK plus 1, which is 2 plus 1 is M3. And then it is, of course, 12.401. And then after that, we can find our V3 is equal to 1 over 12.401 multiplied by 1.224, 5.302, 12.401. And then we can have the answer is 0.099, 0.428, and 1. Now we can put everything in our table. So now for k is equal to 2, V2 is 0.237, 0.638, 1, and A multiplied by V2, we will get 1.224, 5.302, 12.401, and then our dominant eigenvalue is 12.401. And if we calculate by using this formula, mk plus 1 minus mk, which is m3 minus m2, we will get 0.11 because we have our m3, and our m2 is equal to 12.508. And then if you minus mk, which is now is m2 minus m1, you will get 6.208. And then now we need to proceed with k is equal to 3. And our V3, we know already this one, 0.099, 0.428, 1. And then we need to calculate AV3. K is equal to 3. We need to calculate first AV3. is equal to 4, 2, negative 1, 2, 6, 1, negative 1, 1, 12, multiplied by your V3 is 0.099, 0.428, and 1. And for this one, what you will get is 0.252, 3.766, 12.3, 29. And of course, for the largest eigenvalue, the dominant eigenvalue is mk plus 1 is equal to m4 is equal to 12.329. And then we can get our v4 is equal to 1 over 12.329 multiplied by our AV3, which is this one, 0.252, 3.766, 12.329, and then you will get the answer is 0.02, 0.305, and 1. Okay, so that we can put in the table. We have AV3, we have 0.252, 3.766, 12.329 here. And then our M4 is equal to 12.321. And then if we want to use this stopping criterion, now we get 0.07. While now our MK, K is equal to 3, our MK is 12.401, which is this one. 12.401. And then M3 minus M2, you will get 0.107. And then meaning that we cannot stop. And we also know that our V4 from the K3 here, 0.02, 0.305, and 1 here. And then for K is equal to 4, we need to calculate we need to continue our iteration. K is equal to 4. AV4 is equal to 4, 2, negative 1, 2, 6, 1, negative 1, 1, 12, multiplied by 0.02, 0.305, 1, and then you will get negative 0.31, 2.87, 12.285. And from here we can know that mk plus 1 is equal to m5 is equal to 12.285, and our v5 is equal to 1 over 12.285 multiplied by negative 0.31, 2.87, 12.285. And what you will get is negative 0.025, 0.234, 1. And then we must put everything. So AV4, what you will get is negative 0.31, 2.87, 12.285, and the dominant eigenvalue is 12.285. And then for this stopping criterion column, you will get 0.04, which is less than 0.05. We need to stop, so that, because we know that our eigenvalue here is M5 is equal to M5. So meaning that the corresponding eigenvector is M5, where we already get it, 0.03, 0.231. So this is our solution for eigenvector, while this one is our solution for eigenvalue. So meaning that if our eigenvalue is M5, and then our eigenvector also must be V5.